back. So let's start the last session of the tutorial session.
Thank you, Geji, for the introduction. Thank you, everyone, for coming back. So, in the first part of this tutorial, we did a lot of learning. Now we're going to add a little bit of the dynamics and the control. And specifically, what we are going to be consider is the framework of reinforcement learning under constraints. So, just as a brief recap, let me start talking a little bit about reinforcement learning before we introduce the constraints, and we delve a little bit more into the applications that Luis brought up early today. So reinforcement learning is, in a sense, a model-free framework for sequential decision-making in Markovian settings, right? So what does this mean? So now we have a state in our system, and this state evolves according to some probability distribution, right? This could be indeterministic, but let's say for the general framework, it could be, it's going to be a probability distribution. And this probability distribution is as follows. So the probability of being at some state at time t+1 only depends on my current state and on the current action, or on the current control input, if you want. And as I said, like, this doesn't depend on how we got to this state at time t. It only depends. It only matters that we are there. So this probability distribution defines the environment, and then on top of that, there is an agent, which is the one that is in charge of selecting these actions, right? And for each one of these actions, two things happen. Again, this transition to a next state, and then there is a reward that is received by the engine that will inform it about the quality of the decision making, right? So this could also be a cost in more classic control literature, but for reinforcement learning rewards, that's the usual thing. And because this reward tells us how good or bad we are, what we are interested in doing is actually on trying to maximize the total reward that we get in an episode, right? So what do I mean by this? I mean that we will have a sum over time, and at each time we receive a reward, and we want to get as much as we can from these rewards. And we have an expectation here that comes from two things. One is the transitions of the system are probabilistic, but also the policy of the agent, or this decision-making rule for selecting actions could also be probabilistic, and therefore we also consider that here. Couple of differences in settings. I'm not gonna worry too much about this in this presentation, but like sometimes I will talk about finite horizons, sometimes I will talk about infinite horizons, sometimes we'll talk about discounted rewards, sometimes no discount. But there is some subtleties and differences for all of those settings, but I'm just gonna put them all together in one, and depending on the application, one might fit a little bit better than the other. Okay, so this is a classic reinforcement learning problem, has been around for a while. There are multiple ways of solving this problem. Basically, two big families of algorithms, one that is related to Q-learning, and then there is another family that includes a lot of the modern methods that is based on policy optimization. Okay? So basically taking gradients of this value function with respect to a policy or some parameterized version of the policy and doing gradients. So what is constrained reinforcement learning? Well, instead of having a single reward that we want to maximize, what we have is actually a series or a sequence or a set, of rewards. Now here in this case, we have m additional rewards. And basically the objective is we want to keep the value of these value functions above this threshold Ci. Okay? So this is the frame. A couple of examples, and going back to the applications that Luis mentioned earlier today, let's think of safe navigation. Okay? So this is not learning safely to navigate. Okay? So this doesn't mean, okay, we are going to be doing trial and error and never collide during that episode. What we are talking about is, at the end of the training process, we want to guarantee that we have a safe policy. Okay? So, in the traditional reinforcement learning framework, right, what we want to do is to maximize this V pi. Okay? So again, it's the expected value of the cumulative reward. Okay? And to do that, we need to define a reward. So in this case, our reward needs to have two components, right? There should be one component that promotes movement to this goal, right? So this, what we have here is some negative distance, some negative of the distance to the goal, square. And, the closer I am from the goal, the more reward I get. So that basically will make this agent learn something that drives it there. But of course, we want to avoid the obstacles. And to avoid the obstacles, what we could think of doing in classic reinforcement learning setting would be to add some penalties. Okay? So, or rewards, okay, depends how you say this. So rewards if you are outside of the obstacles or in the free space, penalties if you are inside. Right? And again, here we go to this distinction once again between constraints and penalization, right? We're going to be discussing a little bit more about this. But again, here, selecting the set of coefficients that gives you the desired behavior might be very tricky. So for instance, if you select -1, right, for all of the obstacles, and you just run this, assuming that you can go through the obstacles, you will end up with some trajectory like this, which is unsafe, right? So all of the trajectories actually collide with this obstacle. So this is not what we want. If I set another parameter, set 2.9, now I get safe trajectories, but these trajectories are not really very optimal, right? They go like quite far from the obstacles. So, they are trading off safety, trying to be far away from the obstacles at the expense of a larger cost. Okay? So typically what one would want in this problem, and we will discuss later on when we see the results, but you will have different values for all of these obstacles. And doing this parameter search in R5 in this case, but if you have more obstacles, there will be more parameters, might get very, very, very complicated. So in that sense, constraints actually give us a much easier way of specifying the problem, right? We don't need to tweak these parameters. We can just say, okay, we want to maximize some reward associated to a task, subject to this condition that says, I want to not collide with any of the obstacles with high probability. Okay? And again, the reward maybe takes this form. As I was showing before, it's like maybe the reward could be the negative distance to the goal, or the negative distance square. And this probability of not colliding, maybe if you want to write it mathematically, it will look like this, right? So what does this say? So this says, okay, we want for all states, right, from time t equals 0 to t minus 1, we want to make sure that at no time we are inside the obstacles, right? And we want the probability of this event to be large, right? So this, as it says here, is some sort of version of, probabilistic version of control invariance, right? So control invariance means that I want to remain in a set for all times. Here, what I have is a probabilistic notion of that. But of course, this doesn't fit, or it doesn't, exactly fit the first formulation that I gave you for constraint reinforcement learning, where actually we had some sums. Dealing with this type of constraints is a little bit more tricky. So one way of going around this is to redefine these constraints, or to relax these constraints, or write them differently, better said, in this form. Where now what we are replacing these probability constraints by something that looks like that. Right? So this is more in the vein of the first general formulation that I provided. And what we are doing here is we are replacing that constraint that goes, that is an intersection of events across time by a sum, right? And this is not tight by any means. But what you can prove is that if you have a policy that is feasible, or something that satisfies this constraint, then it will also satisfy a constraint that has the intersection. Okay, this just follows from some union bounds and doing some negations of these probabilities. The thing to notice, perhaps, is that instead of having this probability 1 minus delta I, here we need to tighten this to delta I over t. So we have similar results in the infinite case, infinite horizon case, but they take a nastier form. But the reason for this is like just to take into account that those union bounds that we use. But the thing is, bottom line is that we can actually formulate this constraint reinforcement learning problem that if I am able to solve it, then I'm guaranteed to be safe, right? Which is very different than the regularized version that I described before, where I need to figure out what these coefficients are, and only after training I can know if this is safe or not. In this case, I start here. I know that if I solve it, I will have something that is safe. So the other example that Luis mentioned, and maybe I'll go a bit faster on this one, is this wireless results allocation, right? So we have a set of different transmitters and receivers. They want to communicate, send some information, and the way that information propagates is through a channel. So the agent X, let's say, has to decide how much power to transmit. And, depending on the state of the channel, if the channel is bad, let's say, no matter if I select a lot of power, maybe at the end of the receiver, the received power is very low and the quality or the rate that what gets transmitted is low. On the other hand, if the channel is good and I'm transmitting with good power, what I get to the receiver will be a signal with high power, and this allows me to have a larger rate. Okay? So, of course, all agents are communicating at the same time. They will interfere with each other, and therefore the rates that they get actually depend not only on the powers that they allocate, but on the powers that everyone allocates. And of course, they also depend on the quality of all the channels. Right? And here the problem is, okay, I want to use the minimum amount of battery while guaranteeing some rate of communication for all the agents. Right? Up to this point, there is nothing Markovian here. Okay, you could think that maybe these channels under some settings could depend on the previous state, so there would be some Markovian aspect, but to make it look more like an MDP, instead of thinking about power, instantaneous power that is transmitted, we can think, for instance, of agents that are mobile and perhaps they have a battery some battery budget that they can use for communication, and every time that they assign some power to transmit, this battery goes down. Right now, you really have a state. If you run out of battery, then you cannot transmit anymore. Right? So maybe we can formulate a similar problem where we want to keep these rates at above some certain threshold, while minimizing the probability of running out of battery. Or, using a similar trick to the one that I used before for navigation, for safe navigation, maybe we can use this surrogate for this idea of not running out of battery. And this is just another application where you can formulate a constraint problem in an MDP setting. There are other applications. We have done some work on power systems for blackout mitigation and stuff like this. But okay, those we are not gonna talk about. So overall, this is the framework. Okay, so again, nothing very different from your regular MDP, but now you have constraints. Okay, and this is gonna make life a little bit easier in terms of formulating problems, as I tried to motivate before, but perhaps it is a little bit harder to solve them, okay? Or perhaps not. So this is the sort of the different approaches that one could take, right? So one is what I briefly mentioned before, which is, okay, we could try to do reward shaping or combine these rewards using penalties, right? But this has some problems. As I've said before, like this tuning of these parameters needs to be done by hand, right? And then, if you solve the problem for a specific map and I just reshuffle the map or I just move the obstacles around, you might need to do the problem again, right? So it also depends on the problem at hand. The other approach that is common in the literature is to use prior knowledge, which of course, if you have the prior knowledge, you should use it. But in general, what we need here is to know that some actions are always safe, or that there is a policy that is safe that we can rely on. So if you have that, I think it's great, but sometimes you don't, right? So in those cases, this you cannot use. And sometimes these projections might be tough, right? So remember, these problems in general will be non-convex. Spaces that you're working with are going to be non-convex, so those projections could get very tricky. And then other approaches that try to rewrite these problems or to approximate these problems using linearizations or other convex surrogates. But here the problem that you may have multiple times is that, okay, you do this approximation, you update your policy, but the resulting iterate actually is not inside a feasible set anymore. It is within the feasible linear set that you approximated, but not the actual set that you're interested in. So if you were here in the first part of the talk, of course, you know that I'm going to be vouching now for solving this problem using duality, right? And again, the benefits are very similar to what Luis and Alejandro discussed earlier today. These formulations are domain independent. They are tractable. I will mention this a little bit more. Miguel will actually discuss in detail algorithms. But again, the question is, can we actually provide approximation guarantees for these problems or not? Given the non-convexity of these problems, right? So let's go into that, right? So let's just a reminder, what is the dual problem? Okay, so we have this Lagrangian, right? So we have taken the constraints, we put them in the objective, multiplied by some Lagrange multiplier, which is in the positive orthant. And what we want to do is we want to solve this problem that consists in maximizing, this objective with respect to the policy, and then minimize with respect to lambda, right? So this is very, very similar. I mean, it's exactly the same idea that we saw in the first part of the tutorial. And as you can imagine, what the conclusion should be, otherwise this talk wouldn't make sense here, is that these problems also have zero duality gap. Okay? So if you solve this problem, the value that you get is exactly the same that you would get if you solve the primal problem. Okay? Now, the reasons why would this happen is actually quite different from what we saw in the first half. Okay? Again, otherwise, it wouldn't make sense that I'm here talking for 40 minutes. Okay? So I want to give you some intuition as to why this happens. Okay? And the reason here is that there is some hidden convexity also in this problem, but the hidden convexity here comes from the occupancy measure. Okay? It's not the idea that Alejandro mentioned about Lyapunov's convexity theorem. Is something somewhere else that this convexity appears. Okay? So let me talk a little bit about the occupancy measure, what it is, and then we can see how it can be used to show that these problems have zero idea. So occupancy measure, right? In a sense, not exactly, but intuition is some sort of average as to where your MDP is going to take you. Okay? So that's the one way of thinking about it. So formally is this expression, but basically what we are doing is we are summing over time the probability of being at a given state and a given action for all times, and we are discounting this by gamma. Okay? So this is the formulation for the discounted MDP. If you don't have a discounted MDP, then it's just the average one. And yeah, this basically tells you, okay, at each time, how likely it is that you're going to be on a given state. And if you are able to solve this problem, actually, if you have the occupancy measure, this is also another way of solving RL problems, which I didn't mention, but if you can optimize for the occupancy measure, then you can also recover optimal policies. And the reason for that is that occupancy measures and policies are related by this equation, right? Sometimes it might be trickier to compute the occupancy measure or to compute this normalization, but there is a relationship between the two. Okay? But more importantly for us, what we care about in this talk is that actually value functions, right? So these cumulative sums of rewards or expected cumulative sums of rewards can be written linearly in the domain of occupancy measures. Okay? So this is the expression, right? Basically, instead of having to look at these complicated sums across time, if I can work directly with these policies tell me pretty much how often I'm going to be in each one of these states. So I can just look at the reward at a single reward, but I need to be able to sample from this occupancy measure. Okay? But this is just an expectation of a reward, which is an integral of the rewards times the variable, times the distribution, sorry, which makes it a linear function in the space of measures for rho. Okay? So this is indeed linear. Okay? But this is not enough, right? I mean, the fact that I can write the problem linearly doesn't mean that the problem in policy space, right, has zero duality gap. And this is, in a sense, a non-proof, okay, of this result, but the non-proof I'm giving it because it will be useful for what follows, okay? So bear with me. But basically what I'm saying is this, right? So, okay, we formulated this problem that we are interested in. So we have this policy here. So this is what we are trying to maximize. And there exists this other problem that, attains the same value, right? P sub rho. P sub rho is equal to P. Okay? So this is just a different formulation. I can solve the problem in this domain, and the value that I would get will be the same. Okay? And this second problem in the occupancy measure, because these functions are linear, actually is an LP. It will have zero duality gap. Okay? So actually I can claim very easily that P sub rho is equals to D sub rho, right? Which again, D, the dual function of the dual problem, is the min-max problem here. But the fact that we have primal equivalence does not necessarily mean that we have dual equivalence. Okay, so there could be, it could be the case that this problem here, when I compute the dual, it attains a larger value than D sub rho. Okay? So pictorially, if you want, pictorially we can maybe look at this example. Okay? So this again, this is a cartoon of the situation that I will also use to illustrate the proof of this result. Okay? So what do I have here? Here I have this set C in red, which is the following: take any policy that you want, right, and observe what is the value, right, of the objective, and look at the constraint. And let's just say that we have one constraint for simplicity. Okay? So because these functions are non-convex, so when I take any of these points, right, any policy, I get one of these two values, and I just mark it here on the board, right? That attains some value v, some value v0. It's just here. So then I select another policy. If I go with all the policies, I can end up filling this figure. So what is P, right? So P, the optimal solution, right, is the maximum value, the maximum V0 that I can get, assuming, or for those policies that give me positive Vs, right? I'm trying to maximize V0 subject to V being positive. Okay? So, okay, positive Vs are the ones that are on the right-hand side. The value or the point that attains the maximum policy, is this one or this one. They are pretty much the same, right? So there are two solutions that could be, right? Now, what is the dual, right? So the dual, if you remember this definition, let's look at this one maybe. So it's this min-max problem, right? So it's min in lambda and max in P. So what does this mean? This means that what lambda defines, in a sense, is, so remember, is V0, right? So it's the value V0 for any policy. Let's say this policy here, V0 is the value that is up here, right? And then lambda is something that is multiplying the constraint, right? The constraint slack. So in this case, it will be maybe V is here, right? So basically you are multiplying this distance by lambda. But basically what this does is it defines a line, right? So for different values of lambda, I will have different lines that will weight more or less the constraint, right? So if I have lambda equals to 0, then, this is going to result in a flat line. If I have lambda very large, this is going to be tilted. This is the role of lambda here. So that's one part. Then the other part is the maximization with respect to pi. The maximization with respect to pi, what it's going to do is going to push this line in this direction, right? And if you look at specifically the problem of pushing the line in that direction, which is the maximization, you realize that this line, regardless of the orientation, right, it needs to lie in some of the extremes, right? And specifically for this value of lambda, okay, the dual value is this quantity here, right? So it's lambda star, which gives me this slope times v plus the value that I get at v0. Okay, so this is where it intersects. Okay, so and this has to be the dual, right? This has to be the dual optimum, because if from there you try to change the slope, right, in one direction or the other, what happens is that this value d actually goes up. Okay, so this has to be optimum. Okay, so this is why for problems that are non-convex. Okay, so all of this just to say that for problems that are non-convex, your epigraph will be most likely a non-convex set. And when your epigraph is a non-convex set, you cannot guarantee that you have strong duality. Okay, so the dual point might end up higher up from the primal. Very different situation happens when you look at the occupancy measure. When you look at the occupancy measure, actually you have a convex set, right? And this is, again, not surprising. What I said before is that I can actually write these value functions as a linear function, right? As linear functions, and therefore it is expected that the epigraph of this problem written in occupancy measure is actually convex. Okay, so, and in this case, again, we have primal equivalence. So we know that the primal of rho needs to be at the same point as the primal in policy or of just P. And this point also has zero duality. Okay? So how do we prove then that actually the problem in red also has zero duality gap? Well, we prove that it has zero duality gap by actually showing that these two sets are the same. Okay, so it cannot be the case that the shape of our original set in policy space is not convex. Okay? So actually, we show this equivalence between these two sets, and from here, once we have the equivalence between the two sets, duality gap or zero duality gap holds directly. Okay? So this is the hidden convexity that appears in this problem. Okay, so it's about showing that these two sets are the same, which doesn't mean, right? So this doesn't mean that the policy space or that these functions are convex in policy. Okay, so it means something a little bit more subtle. Okay, so in again in occupancy measure, if I have two policy or two occupancy measures, rho 1, rho 2, right? Then if I take any point here in the middle, I do this linear, this convex combination, but sorry, for any alpha, I actually have that the value function that I attain is alpha times v of rho 1 plus 1 minus alpha times v of rho 2. Okay, so this is because, again, linearity. In the second case, or in the case of policies, this statement doesn't hold, right? So if I take P1 and P2 here, and I take a linear combination between those two, I cannot guarantee anything about the value of lambda, of alpha P1 plus 1 minus alpha P2. Okay, so this policy could be anywhere. The policy will be here, but the value function could be anywhere. And this actually gives us some problems when we are thinking of conversions of primal dual algorithms. And Miguel will discuss this a little bit more. But what we can say though is that for any alpha, okay, there is some policy, okay, which doesn't need to lie in this line. It could be somewhere else, right, in this set. But there is a policy in this set that actually attains this value. Okay? And that's basically because for each policy we have an occupancy measure and vice versa. Okay? So this is how this result gets proven. Again, a sketch. This is not really a proof. Okay. So again, touching on one thing that I didn't make too much emphasis on is that these problems or these solutions, these theorems that I just considered, we are just talking about maximizing policies over the whole space of policies. Okay, this could be anything that you want, but in general, this is never the case, right? Unless you have a very small set of discrete state action spaces, then yes, you could do it. But in general, what you're going to have is parameterizations, right? And these parameterizations are non-convex, and therefore this is going to introduce some sort of duality gap. Okay, very similar to what we saw earlier to it. Okay, so nothing changes here in the formulation. The only difference is that instead of maximizing over a class of policies, we are maximizing over a class of parameterized policies. And the theorem says something like this. The theorem says that if we have a class of policies that is rich enough, okay, and again, rich enough I will define in a bit, then we can bound the duality gap, okay? And we can bound the duality gap by something that looks very similar to the bounds that Alejandro and Luis discussed earlier today. So let me go a little bit more in details about this result. So what we say is that this learning parameterization has to be new universal. Okay? So what does this mean? This means that the total variation, right? So the total variation, so the total variation here between policies, right, from the space of all policies and the parameterized policies needs to be bounded by nu. Okay, so this is an integral that is done over A. It needs to hold for all states, and this in particular for the worst case scenario. And this nu here appears also in the bound in a similar way that appeared earlier in the first part of the tutorial, right? So if I have a very, very good parameterization, basically it's something that takes nu very close to 0, then I don't have duality gap, right? And we recover the previous result that we had. So not surprising. The second thing that appears here, similar to the first result that we had, is the Lagrange multipliers, right? So once again, the hardness of the constraint, how hard it is to satisfy the constraint, will make these bounds to grow. And there is one difference here, which is associated to the fact that we are solving this problem sequentially, okay? Which is the discount factor, right? So we have this discount factor that appears here, and it's not surprising that it's there, right? So if you think about it, or one way of thinking about it is that supervised learning, right, is a sequential decision-making problem where you only have one decision, right? So, that corresponds to having an horizon of 1, which is the same as having a discount of 0. Right? So if your discount is 0, then you only care about that first instance. And in that case, this gamma disappears, right? In this case, because we are doing sequential decision-making, we need to accumulate errors. So each one of these policies will introduce a little bit of an error, and therefore it's not surprising that this term appears here. So again, basically to summarize what I've said so far, and actually before I leave the floor to Miguel to discuss a little bit more the algorithms. So when we are considering, so two things, right? So the first thing is like very similar to the first part of the talk, right? I want to push the idea that looking at problems with constraints makes sense from a design perspective. Okay? It's easier to formulate those problems, and it's not so hard to solve them. And again, Miguel will talk more about algorithms. And the only thing that one could be worried about in this particular case is about the approximation guarantees. Right? So if I go into a dual domain and I solve the dual problem, okay, how good is my solution, right? But what I showed you is that actually we also have zero duality gap in these problems, or small duality gap if you are considering parameterizations. But the reason why this happens, right? So the reason why this duality gap appears is very different from what we had earlier today. In this case, actually, what happens is that we are exploiting, this reformulation of reinforcement learning. We are reformulating the problem or we are looking at the problem. We are not really reformulating the problem. We are looking at the problem from the occupancy measure perspective, and we are exploiting some of the properties in that domain to show that actually the epigraphs of both problems in policy and the occupancy measure is known that it's convex, but we are exploiting this relationship to show that these sets should actually be the same, and therefore strong duality holds. So that's that. And yes, and again, if you have some parameterizations, you will have some duality gap that appears based on the quality of your parameterizations. So with that, I will wrap up here, and I will leave it to Miguel so that he can discuss a little bit more about the algorithms for these problems.
So we saw the theoretical properties, basically, of CRL problems. So if you paid enough attention during the first half, you should know more or less what's going to happen now, right? So we saw that CRL, right, even though it has a complex structure, constrained reinforcement learning, it's a non-convex problem, still has zero duality gap, right? So strong duality holds. So if we wanted to go about solving this, right, we should go through the dual domain, right? And here, basically, we will write the dual function, basically the minimization over the dual variables of the maximization of the Lagrangian. right? So here we can make the first observation, which is that we can rewrite the maximization part of this dual problem as a standard reinforcement learning problem, right? So if you pay attention, we have that the Lagrangian is basically the objective reward plus the reward of the constraint, right? Like the constraint violation multiplied by some multiplier, which this structure would allow us to define a new augmented reward, right? So a reward that's the reward of the objective plus the lambda. Here I have a single constraint, but if you have multiple constraints, the sum of the different dual variables multiplied by the reward of each constraint that you have, right? So we would have a primal step in this primal dual or dual algorithm, right? A primal step that just looks like your standard reinforcement learning maximization. So potentially you could throw here your favorite method to solve this maximization. Then the second step of this dual algorithm would be simply to update the dual via dual descent, right? So basically you take the gradient of the Lagrangian with respect to the dual variable and perform dual descent on it, right? So here you would have a distribution which over which you need to do policy evaluation, which you do by with the policy that you have acquired in your primal step, right? So primal step maximization, standard vanilla reinforcement learning, dual step, dual descent, equivalent to policy evaluation. In practice, these expectations, you want to get rid of them. How do you do this? Well, for example, you could take a policy gradient, but here you could take like a more complex or more complicated, more modern method to perform this maximization. But imagine that we take a policy gradient and then you do policy evaluation by extracting a trajectory of this policy that you have acquired on your primal step, right? So nothing here should be surprising. This is just a primal dual, primal step. This gradient, since it's in reinforcement learning form, takes this policy gradient form, right? So if we perform this form of dual descent, this dual algorithm, whereas the output of this maximization, we obtain some form of raw approximate solution, right? So we are performing this maximizer up to some raw accuracy, right? So we maximize up to a certain point of the global maxima. What is the type of result that a dual descent algorithm will provide? Well, then what we know is that after a finite amount of iterations with some fixed step size, the iterates that we generate will provide us with some duality gap, where here, this is exactly the same duality gap result that Santiago presented earlier, and then our error in the maximization gets added linearly. So this is good news, right? So if we can do very well and we can maximize this function well, the error just gets added linearly. The better that we do, the smaller that this gets, right? So we are able to do dual descent without any additional issue in the constraint reinforcement learning setting. Okay, so what does this point in the duality gap translate in the interest of our problem, right? In optimality and feasibility, right? So if we do this form of dual descent, right? So the sequences that we generate can be shown to be almost surely feasible. So with probability 1, we will generate sequences that provide constraint feasibility, right? And will be near optimal. So the sequences that we generate will reach the optimal point of the primal optimal point with some error that depends on our step size and some bounds on the gradients, right? So basically with probability 1, we will generate a state action sequence that provides feasibility and near optimality. Okay, so we have a potentially working algorithm can we throw this primal dual or dual descent to a problem? So this is the navigation problem that we showed earlier, right? To which we have simply thrown a dual descent algorithm, that's the one that I showed in the previous slides. So basically, we have one constraint for each of these obstacles, and we are asking the algorithm to not hit the obstacles with probability 99.9%, and the objective is to move to this goal as fast as possible, right? So we run this algorithm, and we see that it provides different weights to, so different dual variables to each one of the obstacles, and basically in the reward, we'll see that performing this dual approach will always outperform any form of homogeneous reward shaping that you do. So any homogeneous reward that you put here for the obstacles will always be bounded, but by what you can do with the dual approach that dynamically places their weights for you. And if we see here at the trajectories generated, here we have the lighter color are earlier iterations, darker color are later iterations as the algorithm trains, right? And we have on the y-axis the safety achieved by the iteration and the reward achieved. So basically, as the algorithm is executed, basically we get more saved and more and faster movement of the agent. And basically here zoom, we see that once the algorithm learns to be safe, then in general doesn't forget to be safe, right? So it approaches the safety region and then it tries to be safe as fast as possible, right? So good, right? Like we have a primal dual algorithm that it works for this navigation problem. So let's try now the resource allocation problem, right? Where here we'll have two agents, two constraints, and we need to assign some power allocation to each one of the agents. And here we are looking at the constraint for each one of the two agents. And here we are starting to see some, let's say, weird behavior or something that maybe you are not expecting, which is, okay, so the value functions here oscillate, the dual variables oscillate, and then the policies oscillate. So these policies are not stationary, right? So here in this problem, I don't learn anything. I generate trajectories that satisfy my constraints. I have some oscillation of the dual variables, but these policies never converge, right? Like these policies are not stationary. They seem to oscillate depending on the value of the dual variables, doing different allocations at different time steps, right? But what we can see is that by this mixing of this oscillation is generating value functions that provide constraint feasibility, right? So what happened? Like I gave you like some form of proof that said that this was almost surely feasible and near optimal. But well, here I didn't lie to you, but importantly, this theorem or convergence of primal dual algorithms in general or any dual method provides guarantees over the iterates generated by the algorithm, right? It doesn't give you any guarantee on the policy that this will generate, right? So what this is telling you is that by utilizing the dual descent method, you will generate a state action sequence, right? So states and actions sampled from the policy, and this policy is depending on lambda, that are almost surely feasible and near optimal. There is no guarantee and there is no claim on the optimal policy that you obtain, right? This is not it's not an issue of the proof methodology. It comes with the fact that you are approaching the problem on the dual domain, right? So you cannot say anything about the optimal policy. The only thing that you can say is that you are generating trajectories that are equivalent to saying like that you are generating policies that are sampling from the near optimal policy, the optimal policy that's close to this bound, right? So here we have the first issue, because if we cannot provide any form of guarantee on the policy, right? If all these dual descent methods in the CRL setting are providing us our state action trajectories, if I want to put this in a system, in a real system, the trajectories to me are useless, right? At the end of the day, I need to be able to stop the training process, take what I've trained, put it on my hardware or whatever system I want to evaluate, and I want to be able to extract these claims. But right now, there is no way for me to stop here and satisfy any of these claims. As a matter of fact, if I stop and I take the policy at any point in time, the outcome of trajectories generated by that policy at that time will not satisfy this, right? So that's our first hurdle to overcome here, which is that while we're capable of generating state action trajectories that are feasible and near optimal, we require let's say that we require continuous execution of this. You can never stop executing this, right? At no point in time you can stop and save this theta and claim anything of it, right? So we have continuous execution of this. So basically this, right? So we cannot recover the optimal policy, right? So how do we go about this? And before I go about this, let me show you a very small counterexample that will help you understand why this is a fundamental issue that you cannot avoid by being smart about the algorithm. Okay, so let's take this very simple MDP, right? Let's take this very simple example, right? You have 3 states here. From state 0, you can transition to state 2. State 2 takes you back to 0. From 0, you can go to 1. And in 1 and 2, you can decide to stay there, right? And we want to find some policy, some monitoring policy, right? That spends 1/3 of the time in each one of the states, right? This using constraint reinforcement learning, very easy to formulate. Basically, you want to maximize the indicator function of being in state R0, subject to that the time spent in state 1 and in state 2 is over 1/3, right? Like this would be the natural specification of this problem that we are asking to solve. So what would be a policy that solves this CRL problem? Well, for example, you drawing actions randomly would solve this, right? If you are in any of these 3 states and you take an action at random, either staying or going to the other state that you can move, then this would naturally satisfy this requirement. This will lead to you spending 1/3 of the time at each one of the states, right? So a policy that does this exists. But let's look now at what happens if we construct the augmented reward of this problem, this regularized reward. So if we try to solve it via this dual descent method or like any of these primal dual methods, the first thing that we do is, okay, we want to construct this new reward, which is the objective reward plus the reward of each one of the constraints multiplied by this weight. That's the dual variable, right? Or this could be any form of your regularized method, or think about it as your standard reinforcement learning method without constraints, right? You are constructing a reward of this form to solve this CRL problem. Okay, so what is the choices of lambda 1 and lambda 2 that you can take? So if you choose lambda 1 to be equal to lambda 2 to be equal to 1, right? So this is 1, this is 1, then all policies are optimal, right? Because you receive the same reward no matter in which state you are in. Then if the lambda 1 or lambda 2, the weights that you are giving to the state 1 or state 2 are smaller than the weight of being in state 0. So if the reward that you receive for being here or here is smaller than being here, and if the optimal action to take is always to go to the state 0. So you will spend 1/2 of your time in state 0. So these weights are not optimal. Then if you put one of the weights to be bigger than 1, that will lead to an absorbing state where you will go to that state with probability 1. So basically, this counterexample, what it's telling you is that the optimal weights are lambda 1 and lambda 2, which are the weights in which all policies lie, right? So even if you have the optimal weight, which is this one, finding the policy that provides you feasibility is not an easy task, right? Like this hasn't solved you anything. Like having access to this optimal value of the multipliers hasn't solved your primal problem. And that's one of the reasons why if you execute this in practice, if you throw a primal dual algorithm at it, what you will see is that the dual variables will oscillate. As they oscillate, this is the choice, the probability of moving to state R0 or staying at R1 in state R1, they're gonna oscillate also. And this is completely unavoidable. There is no way you can avoid this behavior, right? So you need to learn to live with this behavior. And if we are unable to remove this oscillation from the problem, because the oscillation is what provides us, the oscillation is what allows you to reconstruct this, the feasibility itself. So if we need to live with this, how do we go about it? Well, we'll do something called state augmentation, but before this, let me give you another reason why this happens, which is, imagine that you are not in the CRL setting, that you are in some arbitrary setting. So if you have a convex function, you could recover the policy, and this might be the method that you are used to. You might be able to recover the policy via dual averaging. So all the realizations that you saw, you average over them, and this, under the convex setting, you can provide guarantees that this point is an optimal point, is an optimal primal maximizer. However, when you are in the non-convex setting, like we are in CRL, this is no longer the case, right? So in this case, you would need to basically memorize the complete training sequence of policies to recover the distribution, right? So the oscillations are mandatory, and the only way that wouldn't require the oscillations would be to memorize completely the training sequencing, which in itself is not feasible, right? Like if you're training for millions of iterations, this would imply you need to store millions of policy parameterizations, right? And then sample uniformly over it to be able to recover the guarantees, right? To be able to satisfy this. Yeah. So that's comes from the gradient. That's the squared expectation of the gradient, if I think. It's the bound of the reward, no? Yeah, it's the square by B is so the maximum reward is B. Okay, so basically what we saw is that at its core, even though they might look like you can transform one problem to the other via regularization or via the Lagrangian, the reality is that a constrained reinforcement learning problem can represent problems that an equivalent reinforcement learning problem cannot, right? There are behaviors that you can specify in constrained reinforcement learning form, but that a reinforcement learning problem cannot specify, right? So then if they're not intrinsically the same, how can we solve constrained reinforcement learning problems? And the reality is that it's in front of our eyes, and we just need to reframe what we are trying to maximize in the maximization step. So instead of taking this maximization step with respect to the state, we can think of it that, oh, let's try to find, instead of state maximizing policies, let's try to find state and Lagrange multiplier maximizing policies. So let's think of the Lagrange multiplier as part of our state, as part of an augmented state, right? So if my solution was to either memorize the complete training sequence or live with the oscillations, can I not learn a policy that knows what to do for every value of lambda, right? So let's include this dual variable as part of our parameterization. So this will introduce some modifications in the structure of our MDP, but let's look at them, right? So any standard MDP, right? We have like the probability transition kernel here, current state, we're going to take some action, next state, right? Normal MDP, and on the right we have the CRL problem, right? So, okay, so to solve this, normally we would find a policy, right, that takes the optimal action given the state, right? But as we said, we don't know how to find this policy in policy space. So instead, what we can do is to find Lagrange maximizing policies, right? So policies that not only depend on the state, but also on the dual variable, right? But now here we need to include the dual variable as input and somehow include some dynamics of this dual variable that naturally they come from the dual descent, right? So we'll have here some dynamics from the dual variable. So we'll have some new probability transition kernel of the dual variables. And now this MDP that was lashed and on top was a normal MDP has been augmented by this inclusion on the bottom of these dual variables, right? So now we'll have an augmented MDP that has a new augmented state. That's the state plus the dual variables that come from the constraint, and a new augmented transition probability kernel. That's the original transition probability kernel plus the transitions of the dual variables that are governed by the dual dynamics, right? But here, it also comes with a fact that in practice, these dual dynamics, they don't need to be a part of training anymore, right? Because we are learning policies for all possible values of lambda. So we can split this process as during training, we learn the policy that maximizes for state and lambda for some distribution of lambdas. And choosing which distribution of lambda is, I mean, the classical issue that you would have with any form of offline reinforcement learning. You could sample them uniformly, but maybe you could have a better distribution for how to sample from these lambdas that might be more sample efficient, let's say. But in any case, you could sample uniformly over a range of these dual variables. And then you learn this policy for all states and lambdas. And during deployment, you simply take actions from this policy and update your dual variables via dual descent, right? So you sample a trajectory here, you run for this trajectory, update your dual variable, then sample from the policy with your new state and new value of dual variables, okay? So basically what we come here, we have a summary of the algorithm, right? Which is what I was saying, sampling policies that depend on lambda, using these actions, and then updating the multipliers. But now we do have an algorithm that in a sense solves the CRL problem, right? It generates a state action sequence that is almost surely feasible and near optimal in the way that I gave you before in the theorem. And here we have two components, right? So we inherit somehow the theorem that I gave you before for dual descent, because at the end of the day, we are doing dual descent. We are just tricking the system by actually learning a policy. While before we were unable to learn a policy, now after this training process, we do acquire a stationary policy in this augmented space that I can take and deploy on my hardware, on my system. It's just that it's not only deploying this policy is coupled with these dynamics, so as to reconstruct this augmented MDP, right? So now we do actually have a policy, and the coupling of this policy plus dual dynamics is what recovers us the guarantees previously, right? Which this is not what you may want though, right? Like ideally we would like a policy, right, that does not depend on lambda, that is feasible and near optimal. But however, like the fact that the value functions are non-concave, and what I showed you before about the need to maintain the whole of the trajectory during training, means that this might not be possible. So there are constrained MDPs for which there exists no stationary policy that will solve it for you, right? So you can construct counterexamples that will require mixtures of multiple stationary policy to produce near optimal and near feasible policies, right? So the fact is that this policy that does not depend on lambda does not always exist. Okay. So now if we throw this state augmented algorithm to the resource allocation problem, well, it behaves as you would expect. It obtains feasibility. This is the margin where you want the powers allocations to go on feasibility. This is the objective. It minimizes the objective. And these here are the policies for the two agents that for different values of lambda, they take different values. But since we know the policy for all values of lambda, this oscillation on the reduced non-lambda space, on the marginalized space, right, doesn't bother us anymore, right, because we have this policy. And let's look now at to get more intuition as to what is happening. Let's look now at a more complex monitoring example, like the one I gave you before with the 3 states, right? So here I have a continuous navigation problem where I have an agent that wants to move around here and it can visit 4 different zones, right? And I'm going to ask it to go to each one of these zones with for a certain amount of time, right? So if I train this problem where I give a reward of 1, the indicator function for being in each one of these regions, and that's the constraint, right? So basically, without dynamics, because I don't need dynamics dual dynamics, I don't need dual dynamics to train, right? If I look at the policy slices for values of lambda, the type of behavior that I get is very easy to interpret for this problem, right? Which is that if the lambda value associated to one of these zones is bigger than the other, then the policy is to go towards that region. So for example, here the red region has a higher dual variable, right? And that slice of the policy is to send the agent towards that region. If I have 2 regions with the same value, then the agent will go to each one of these regions depending on the closest region, right? And you can imagine how mixing these policies for different values of lambda can produce any form of feasible occupation measure, right? So I could ask the probability to be here to be 0.2, or I could ask 0.3, anything that is feasible. So this is basically changing the C value here during the dynamics, right? Because this C value is not part of training. I can now change this value, and any value of them during runtime will generate an occupation measure that, as long as what I'm demanding, as long as the C value that I'm demanding is a feasible value, I will generate an occupation measure such that my requirements are satisfied. So I'm basically feasible and plus near optimal, right? So, and this is what we see for this example that I'm requiring here. This is the occupation measure, and here I see the output of training. Here these lines is telling me how much I am asking of each one of the regions, and these are 100 realizations, and the shaded line shows the worst realization and the mean value of them. So what we see is that for all realizations, they always end up being feasible for all realization, right? So which is part of this probability one result, right? So if you let this run long enough, all trajectories will end up being feasible. So again, we can see the average value of the dual multipliers, like as we have been discussing. It also shows which one of the regions is more demanding. So the red region is more demanding. I'm demanding 20% of the time there. So larger average values of the dual variables. But if we focus on the instantaneous variable of the dual variable during a very short slice of time, we can see that they're going up and down. These oscillations still exist, but since I have access to the policy for any value of lambda, these oscillations don't bother me. In fact, they're necessary for me to be able to maintain feasibility. Okay? So with this, we'll conclude. And basically, we have seen that constrained reinforcement learning, or this approach, is a tool, and we'd argue that it is the tool for you to introduce requirements in reinforcement learning problems, right? And what we have seen is that while you might think I can always use a regularized reward to obtain any form of behavior, there is a whole deal in reinforcement learning about whether the reward hypothesis, even if a reward can represent all type of behaviors. Here you have seen an example where a simple reward, a simple regularized reward, or a weighted sum of rewards cannot represent certain classes of behaviors that CRL can represent, right? So it's not, they're not equivalent problems. CRL can represent more problems. And this comes with other complexity and lack of convergence, but using like this simple but yet elegant state augmentation technique, we can get around this lack of convergence and use policies that solve constrained reinforcement learning problems. Okay, so with this I'll conclude. I'm going to call Luis again to give you some summary of the tutorial, and we'll have questions later. What? Oh.
Actually, maybe this is a good time for all of us to go on stage together, which has not happened yet. Okay. No, yes. Yes. No, I mean, we haven't practiced, but I'm sure, we're all South American / Hispanic, so I guess it works. Yeah. So no, I mean, this is just some housekeeping again. Like I showed in the beginning, this is a little bit of the things that we mentioned. You can go on our website and catch those slides, which has all the references and things, and everything we've talked about today, including the slides we skipped over, right? So that you can go look at what happened and go read the papers and everything else. I am going to, as suggested by somebody earlier, include also a full summary of the bibliography that we mentioned here. Apparently this is useful. You can definitely do that on the website as well. And with that, we would like to thank you for coming. While we take questions at the end here, both about the reinforcement learning part and about the first part, we have plenty of time, so I hope you have saved a lot of questions for the end now. Please go here and answer our survey about today's, tutorial, just for us to have an idea of whether and how much this was useful, or, as Alejandro said, a waste of everybody's time or not. Just so that we know how much, at least, right? So that we can, also get a little bit of your feedback on this. So with that, thank you very much, and we'll be taking questions now.
First of all, do you hear me? Okay. So I had a question on slide 16. So basically my question is there more to the equivalence between these sets C and C row more than the fact that there's a bijection between pi's and rows?
No, that's it. I mean, I guess yes. For every pi you have a row. For every row there is a pi that generates. Yeah. I mean, as long as as long as it's a feasible row, let's say, that respects the transitions of the system, right? But yes.
The really important reason to highlight this is like what appears in the next slide, which is that these sets are convex in different ways. Because there are papers there that tell you that V of pi is a linear function of pi. These are, okay? And that's not true. I mean, V of rho is a linear function of rho. And that's what Santiago highlighted, right? That you can go from rho 1 to rho 2 by tracing the convex combination of rho, and that will give you the convex combinations of V's. But you can't do that in the policy. And that's like a very important limitation or a very important complication of constraint reinforcement learning, because the whole reason why we need to do these state augmented algorithms is because we cannot take the average of policies and realize the average of value functions.
Makes sense. Yeah. I think that was also interesting to point out. I think the second question is more of a philosophical question at this point. It has to do with the second part. When you say that RL is a subset, but it's not a complete subset of CRL, is that sort of taking aside that the reward hypothesis is not true? Because in some sense, when you say a reward of this form, which is a weighted sum, doesn't work, it doesn't mean that any reward wouldn't work. The space of rewards is even larger. So it's just a philosophical question. Are you sort of negating that?
So I'm the oldest one, so I'm the only one that can't get in trouble here. So yes, the reward hypothesis is wrong. Yeah. The counter example is there. I mean, it is elemental, right? I mean, you want to spend 50% of your time on, I don't even know if you remember the example, but you have this space and you want to spend 30% of your time here, 30% of your time here. There is no reward that you can construct that will generate a reward.
That behavior will be the only solution for the problem. That behavior is definitely a solution for the problem, but all of the policies also are.
Yeah. The issue is that you have no way to find it in the set of all possible policies.
Yeah, you can do the following, right? I mean, you can create the reward 0 for all.
That's right.
0 for all states. A particular solution that maximizes that reward is that you spend 30% of the time on each set, but also that you spend 70 and 10. You know what I mean? So yeah, technically speaking, if you wish, the reward hypothesis is true, right? But at the same time, mean.
I see. Thank you.
But that's not their position; it's my position.
Yeah.
I mean, the argument is that you can always include time, or you can include anything. I can model anything by reward if I blow up my state space to be everything. That's kind of that's kind of the thing, right?
The Markovian reward is also.
Yeah. So if you don't have time in this case, no, you cannot represent this type of behavior.
Yeah, the complication is that always the problem with this is like, what's the exact statement of what you mean by the reward hypothesis? If I am allowed to do state augmentation, for example, I can solve this problem, right, on a different state space, but am I changing the problem or not? I don't know. I mean, again, this is the problem is the fluidity of what is meant by exactly that. But ultimately, yeah, I mean,
that's even the word task. Like each paper defines its own definition of what's a task, what's a behavior, and it's like.
But in the certainly, right? I mean, the problem we're talking about the reward hypothesis is what do we mean? But in its basic statement, it is understood to say that like for any MDP and any behavior that you want to induce on that MDP, it suffices to craft a proper reward. That is very obviously not true.
You want to weigh in on the reward hypothesis? No, wait.
About the
the second part with the dynamic kind of policy, yeah, or the state augmented policy. Just one maybe question. So it may be tricky, I guess, to install this, let's say, on a robot that maybe is running. One particular maybe point here is that in order to update this second state, this lambda, so you need some model of the, I guess you need the reward function, but I just wonder whether, there are any other assumptions that you need to have in order to say, okay, I can actually put this on a robot, as opposed to I'm just taking just a policy that says, okay, look at the state, the current state, and give me what's the current action. And that's, I don't know, some neural network policy. Yeah.
So the policy depends on the state and lambda. Okay. So at time t, I have some state and some lambda. Then I can run my policy that I've trained. I run it for T0 iterations. I collect T0 rewards of the constraints. I compute this, the feasibility. I compute this update basically. So I sum all the rewards that I see. I compare it with the amount of constraint satisfaction that I need. Then next iteration, I take the policy for my new state and the new value of lambda that I have just computed. This will give me a new set of trajectories. I get T0 of them, then I do the same thing, right? So you don't need a model or anything, right? You just, so if you have a robot, right, like the robot will move for T0. After T0, it updates the lambdas. It has a different policy, T0, etc., etc.
There it's also, so okay, here you're taking T0 steps, right? And T0 is important because T0 actually gives you enough time for you to estimate the value function, right? That's also the hypothesis that it's, that we didn't discuss much, right? But that's the intuition, right? If you only take one step, right, you are changing the policy at every step. You have no stationarity whatsoever. Your estimates, they cannot be good, right? I mean, like that could be a problem. I mean, if something happens that, like one step updates give you good estimations of your stationary policies, of your stationary rewards, then sure, you can just apply that. But in general, you will need some sort of hypothesis that you need to run a fixed policy for long enough. Otherwise, this quantity that is there is not really the gradient of the dual, right? It's just like some very bad approximation.
Again for the talk. So I got some general questions with respect to the safe RL part. So in safe RL, there are some other probably more towards like practical and empirical algorithms such as trust reason method and like barrier function methods and also like projection based, etc., etc. So how does your algorithm compare with this one? And also another question related to the literature is I have recently come across one interesting paper called Lagrangian PID control for safe RL, where they also mentioned something about oscillation. And then when introducing like integration and like a derivative parts for the control, it's kind of like stabilizes the dynamic and make it converge, like have a better convergent behavior. So I was wondering whether that might be applicable to this case where you can fix the oscillation.
Yeah, let me start with the second one. So yeah, I mean, like here, the type of update that we are doing is just like a one step, right? I mean, with stochastics, we are just observing the current constraint violation and we are updating the Lagrange multiplier based on that, right? And we have some theoretical guarantees that works. But of course, like, like when you have dynamics, maybe like just using, so that's sort of equivalent to using a proportional controller, right? But in some cases, like it might not be the best, right? And I guess like it will depend a little bit on the system itself, right? So, but there will be some cases where for sure incorporating some integral component could be useful. Do you want to add something?
Like this goes hand in hand with what in the first half of the talk, Luis and Alejandro were saying, right? This in this case, the the dual descent that we're doing here is just a stochastic gradient, but you could use fancier methods, right? Like the same way that in the first half, they were saying like, oh, you could use Adam. You just need an estimate of the gradient, right? In this case, I'm not very familiar with the PID Lagrangian, but if it follows the same structure, in a general control is going to be a PID for estimating the gradient of the, yeah. On the update. Yeah.
Just you even stack on top of everything, and then you get to say something as well. Yes, just so that everybody speaks on this. I think, look, you can, just to answer your question directly, you cannot avoid oscillations in certain cases. Okay, for the monitoring problem, it's unavoidable. So it doesn't matter what algorithm you put, there has to be oscillation for you to satisfy the constraints. For the exact reason that Miguel explained, right? There is no static reward that will give you a feasible solution. Only a feasible solution, right? There might be other solutions that are not feasible. So, I'll let you think about that a little bit because this is not, but this is the problem. In SafeRL, maybe it works. In other cases, it doesn't matter what you throw at it. And ultimately, I think the interesting thing about like the connection between PID and these controllers is very interesting. Ultimately, the dual ascent we do is an integral controller. Obviously, you can add a derivative term, which is going to look like a momentum. And that's what? Anyway, yes, it's not important. And so, yes, you can do fancier methods, but ultimately there's it's on the, okay. I'm gonna fix this and let Santiago answer your first question.
No, you are hitting like on a crucial point here. Reinforcement learning is not a linear program. Okay, that's important. Okay, so reinforcement learning formulated in occupancy measure is a linear program. Formulated in policy space is not a linear program. Okay, but the epigraph of reinforcement learning is equivalent to the epigraph of a linear program, and for that reason, a lot of the behavior of algorithms for constrained reinforcement learning is like the behavior of constrained learning algorithms for linear programs. Okay, and I'm not sure if you are still with me on that statement. Okay, but let me repeat. Right. So, first important fact: this is not an LP. Okay, but algorithmically, the properties that the algorithm has are like properties of an LP. Okay, and that's what creates a fundamental challenge in terms of developing a good algorithm for solving this problem. And in that sense, the following are true statements. There are reinforcement learning problems that cannot be solved with dampening, like in those papers that you mentioned. I know which paper you're talking about. One of the ethos is, well, doesn't matter. Yeah. I know exactly which paper you're talking about. So in this paper, there is dampening in the dual domain. They talk about convergence in the primal domain, and then they fall into the fallacy of describing the value function as a linear function of the policy, which, as we argued here, that is wrong. So in that paper, you don't really have conversions of primal variables. You have conversions of duals, but the conversions of duals does not imply the conversions of primals. Now, but what they say is also true. I mean, there are like a plethora of algorithms that you can use to solve what in LP is called the issue of primal recovery. Okay? So that's where there are opportunities for improving upon this and opportunities for research. So there are primal recovery algorithms that we haven't investigated that could be used here to come up with something that doesn't require state augmentation, which, as KG pointed out and Santiago explained, has limitations in practice.
There was one more question about the use of different algorithms for like projections.
Yeah, so that one, I mean, like we touched about, on that like very briefly at the beginning. I think there are many things that will depend a little bit on the setup that you have, right, and how much information. So like to construct, for instance, you mentioned barrier functions, right? To construct those functions, you always need some sort of information about the system, right? So depending on how much information available you have, you might be able to do that or not, right? So if you don't have it, then, you know, like, yeah, I would say like you probably lose most of your guarantees. Similar with approximations, right? I mean, like, depending on how good your approximations are, you know, like once you update your variable based on these approximations, if your update is still in the original feasible set, then maybe that's good enough. But you don't have this type of guarantees in general. And I don't know, for instance, just as an example, right? In the proof of CPO, like they have like a very nice proof in the case that they can compute the solutions exactly. But when they go into the linear approximations, which is what, like the way that the algorithm is implemented, right? Then the guarantees there get a little bit weaker because precisely they cannot guarantee the feasibility on all of the iterations. So, yeah.
No, there was just Andrea had raised their hand, and maybe then we can take questions offline as well.
Thanks a lot. Very interesting. A quick question on the formulations that you chose to study, because it seems to me that a lot of the complexity that you're facing comes from the way you decided to formulate the constraints, which for the problems I'm interested in, that's a bit of an overkill. Because typically in robotics, which is my field, I'm interested in having constraints that are pointwise in time, not summations over time. And I think I've read some papers that were dealing with that kind of formulation. And there things are much simpler. And it seems to me that, well, duality would hold, and doing the normal dual ascent trick with the alternating ascent-descent would provide you a stationary policy that would solve the problem. Is that intuition correct?
No, I mean, I don't know exactly what is what problem specifically you have in mind, right? But for instance, for the problem of safety, right? Like, I mean, like just one time instance wouldn't cut it, right?
I mean, you have multiple constraints, but instead of having the summation of Ri.
Also, you have one constraint for each time step.
Yeah, R0 greater than C0, R2 greater than C2, R3 greater than C3, and so on and so forth. So you have one constraint for each time step.
Okay. But then yes, but then you will have like a huge number of constraints, yeah, right? Which might lead you to other issues in terms of how you solve the problem, right? I mean, so that could be.
But maybe I'm in a finite horizon setting.
Finite horizon, maybe you, yeah,
more
maybe
tractable.
I wanted just to add that I mean, this might be overkill, but this kind of is the natural generalization of, so that's kind of why we focused on this. But yeah, I can understand why this can be overkill for depending on, yeah.
I think that what you have in mind is for all t. So if you want to satisfy something for all t, that's easy because you just impose it on the output. If you want to satisfy something for some t, that's actually more difficult than this. For all t, yeah. If you're thinking all t, yeah, that's easy because you just impose it on the output.
It's a little bit like in the supervised learning problem, right? I mean, if you want to impose constraints on the parameters or on the A directly, that's much easier than imposing it in like a more, yeah. So absolutely. Anyway, so we are still here for. I mean, we ran out of time a long time ago, so we're still here for a little while. Please answer our survey again, and we're gonna be here around and we're gonna be in the cocktail talking about all of this. So thank you very much for coming.
Thank you.